Hello everyone, happy and very good morning to everyone. And hello Principal Sir, Vice Principal Sir, HOD, and all the staff members and students who have joined of the Lakshmi Srinivasan College of Engineering and Technology. I'm happy to share my the RF and and its application in biomedical field. So I think I can start right now. You can feel free to stop me in the middle of if you have any questions. Okay. Okay. So we are today going to discuss a little bit brief on radio frequency and how the radio frequency is implemented in the biomedical devices. So my name is Sri Vidya Palanisamy and I'm an RF engineer in California. Okay. So today's agenda is like what is radio and how do we get here, and a little bit about the conducted RF and radiated RF, the reasons what is the emission happening because of RF, and how do we measure it, both the emission and the immunity of the system, and how do it involved in the medical devices, that is nothing but which is implantable on our human body, and a little bit about the network which involved in the processing of our biosignals to the outer world. Okay, so let's start from the basic. It's radio. So radio is nothing but radio broadcasting is transmission of audio signals by radio waves with a wide distance to the wide audience. So that can be both amplitude modulation and frequency modulation. And what is radio waves? Radio waves are nothing but it's a type of electromagnetic radiation with a specific wavelength. It depends on which signal, like is it a phone signal or just a plain radio signal or a satellite signal, depends on that in an EM spectrum. So what is electromagnetic waves? It is nothing but RF waves that is happen because of oscillation rate of an alternating current or voltage in a magnetic field or electric field. Sorry, I missed. Electric field or electromagnetic field. At till now they introduced from till 300 gigahertz. So it started from 20 kilohertz. Now it's up to 300 gigahertz. So this RF can be transmitted via both coaxial cable, that is up to a longer distance it is covered, but the frequency is limited. You can send up to 1 gigahertz. And the other transmitting method is wireless transmission. So that is widely used across our world, and nowadays you can see many devices and many applications in this wireless transmission. So hope you get a little bit understanding about electromagnetic transmission. So you can see the bottom graph which shows both the magnitude, electrical and the magnetic field covers at both the electromagnetic waves. So as I said before, it is conducted both in the coaxial cable as well as the wireless transmission. So when we take about the coaxial cable transmission, the RF is conducted in a very longer cable, like N-type connectors or something like that. So which is the cable defaultly involve both the cables as well as the connectors. So both the connectors and the cable will have a losses, and sometimes it will be mismatched in the impedance. So when we start a system, first we got to confirm the cable and the connectors are impedantly matched. So what is impedance match? It is nothing but there should be a match between the load from the signal which is at the input side as well as the output side. If there is no impedance mismatch, so what will happen is the signal reflection, for example, the signal will be reflected from the output side and get back to our input. Sometimes the efficient power transmission will never happen. So sometimes, in previous generations, sometimes we used to see in our old TVs that, sometimes that lines, the white, red and green, those lines will pop up in the middle of our transmission. So it is because of that. So the common terms which will be used to calculate this impedance mismatch both on the connectors and the cables are VSWR, return loss, reflection coefficient, cable loss, and transmission efficiency. So even the cable manufacturers as well as the connectors manufacturers both should know everything of this, and it should be very less with all these parameters when you bring out the cables or connectors to the outer world. Next, the second part is radiated RF. It is through wireless technology. It involves antenna, transmitting antenna gain, propagation path and characteristics, path loss, system design, and receiver antenna specifications. So what is antenna? The device that transmits and receives that radio waves. So any current carrying wire creates a magnetic field that circles in accordance to the right hand thumb rule. So time varying electric and magnetic field that are coupled each other orthogonally will create the emission, that is electromagnetic wave, parallelly. So when we develop an antenna or a patch antenna in a circuit, so we frequently talk about antenna frequency. It is nothing but frequency of the radio waves. So relative strength of the antenna, it is nothing but some of the antennas are directional or some of the antennas are omnidirectional. So omnidirectional is nothing but it's like a globe kind of thing. So where the relative strength will be equally spread across the sphere. Sometimes the directional antenna covers at specific direction. So only the strength of the transmission will be higher only in certain directions. So this pattern which I explained in the bottomed image has taken from at one frequency, at one polarization, at one cut. So there are different types of antennas. That is monopole, Yagi. Yagi is, I think, most of our people will have the opportunity to see this because it's like a very old one. And the dipole, and the loop, and bounty, and dish antennas. As I said before, antennas covers both omnidirectional and directional. So the antenna types which I explained before comes under this two. So the monopole, dipole and the rubber duck antennas comes under omnidirectional. Omnidirectional is nothing but in the bottom image, the green circle which says the isotropic antenna, that shows the relative field strength of the omnidirectional antenna. It will be right around the antenna. Like the pointing arrow which is on top, that is the antenna, consider it as antenna, and then that is the sphere which has the highest emission. And the dipole antenna, that is nothing but the directional antenna. It has both Yagi and parabolic and patch antennas. So the basic thing when we build an antenna or when we inbuilt an antenna in our circuit, we first we need to look for the antenna gain. So the antenna gain, it defines the degree to which the antenna concentrates radiated power in a given direction, or it could be a receiver, like it absorbs the incident power from whatever direction, or such as it can be directional or it can be a monopole antenna. So they will first measure with the reference antenna, and then they'll check with the antenna under test the gain of it. So the second thing which they'll be talking about is propagation path. So as you see in the bottom image, the bottommost, so the transmitter and the receiver. So sometimes this transmitter can transmit to the satellite like a space wave, or sometimes through the ground wave, or sometimes it will be reflected from the sky, the ionosphere. So that is a sky wave. So depends on this, the propagation path and its loss will vary. So that we'll see briefly in the bottom slides. So the propagation path is transmission channel between two receivers. And the path loss are varied from reflection, diffraction, scattering, interference between two or more versions of the transmitting receiver. Okay, this is just an example. So consider we have a 4 location and trucks are in the 4 locations. So the pole is the antenna, and the location 1 will have only the free space loss, and the location 2 which will have the free space loss, as well as the location 2 because it covers little more distance. So we have extra path loss that is added with this, and then the plane earth loss. And the location 3, it says free space loss, and the location 3 free space loss, and the plane earth loss, and the diffraction loss, because we have trees or sometimes buildings or something like that. And the location 4, suppose if we are traveling in hilly ranges or something like that, so we have a diffraction losses added to it, and along with the earth loss and the free space loss. And the location 5, it's very difficult to get the signal. Loss will be prediction. Okay, so the next thing is system design. So when you design a circuit, either it is a medical device or any routing devices, so we'll mainly deal about effective transmitting power, because everybody needs it, because we are not simply making a device just to work like within the inches or within certain millimeters or meters or something like that. We need that device to cover at least some kilometer of distance. So we need an effective transmitting power on all the time. So we need this calculation to be done while doing that. So the effective transmitting power, which can be calculated by the transmitting power and along with the cable and connector loss plus the antenna gain. So the transmitting power, it's nothing but the power will be given in dB. dB is decibel. So what amount of power you're sending it from the transmitting antenna, and including the cable loss and connector loss. Connector loss and the cable loss is nothing but from the antenna, that is from the transmitting antenna to the signal generator, what kind of signal you are making it. So the connector between that, connectors and cables, and the antenna gain. Each antenna has its own specific gain by default when you purchase it. So this all comes to give you the effective transmitting power. And the second thing is propagation loss. It's nothing but free space loss. The previous location uh, location slide, so you might have seen the free space. Hope you have an idea. So this can be calculated with the frequency and the distance which covered by the receiver system. And finally, the effective receiver sensitivity. That comes like again the antenna gain, because the receiver side also you will have a receiver antenna. So that antenna gain, and again the cable loss, because the antenna will have the cables next to it to connect it to your programming system or something. So that cable loss and the connector loss and the receiver. So now we know about what is RF and what is radio waves, and how do we transmit, and what are the problems which will happen, but eventually it will be solved by the design of the circuit. So what else could be the problem for the RF signal which is transmitted after the transmission? Or what is the reason behind it? And how do we fix it? So these are the questions next we got to concentrate. So like I said, interference are nothing but the disturbances of the RF signal which is transmitted from the transmitting side, and before reaching the receiving side it will get disturbed. That could happen because of any natural radiators or any unintentional radiators, or sometimes barely by intentional radiators. So natural radiators, okay. So natural radiators, it is nothing but like a rainy season. Think about like if it is heavy rain, each raindrops can reflect your transmitting power. So sometimes if it is a weak signal that you are not maintained at the transmitter side, so that could be a weak signal, and when it is thunder or lightning, so that could maybe result as a radiator, and it will radiate it to the opposite direction, so you may not receive it anything on the receiver side. And the unintentional radiator or incidental radiator is not a purposeful radiator, but it happens unintentionally. That is, an unintentional radiator is any device which creates radio frequency energy within itself, which will be unintentionally radiated from the device, that could interfere the other electronic devices. So the RF devices, up to some extent it will work properly, but if you make it work beyond its dynamic range is the threshold level of that device. The common example is like if the device environment reaches above this temperature or above this humidity level, then it may not work as a regular device how we expect. So at that time the system will behave differently. So that level is called the level which it crosses its threshold level, so it overreacts itself and it will start radiating. So that level is called dynamic range. And if you buy any equipments like spectrum analyzer or network analyzer or whatever it is to characterize a signal, so each equipment will have a dynamic range or spurious-free dynamic range. So you should not run any device beyond that level. Then it may create an unintentional radiator. And sometimes natural EM expose, or sometimes it could happen because of any physical damage to your equipment or your circuit. So in the bottom graph, if you see, The normal waveform that I need to know is the dark green line. That is the real signal. But I am getting additional spurious or additional intermodulation signals in the middle because of my devices performing beyond its dynamic range. So this could improve more and makes it worse to its environment if you are not monitored it correctly. Okay, so how do we build a system that function properly for a long time without any disturbances? So who will monitor all those emission or all the standards of the device? Most of you might have seen that the FCC mark behind every electronic items, or sometimes EN, or sometimes IEEE or something like that. So those are the standards which are made by a professional committee association that says, so if I am making a cell phone and it is obviously it will communicate through wireless, and the committee or the professional group will make certain levels. So my device will be tested in their laboratory and they will measure the emissions. They will make my unit work and they will measure its emissions and they will measure its immunity level, and then they will have a standard. So there will be a limit for any unnecessary radiation that is coming out of your device. So that is called EMC standard, electromagnetic compatibility standards. That is actually, it is like we have many standards in the world. So each country has its own frequency range and its limitations. So if you are going to ship your device to a country, your device should pass their standards and their regulations. Then it should be certified with their country standard and it will be labeled, and then you can sell it inside their country or export it. So that's what I have mentioned in this slide. So the EMC standards define the frequency range and limit of unnecessary radiation to prevent telecommunication and broadcasting devices or any electronic devices for being interrupted, causing interference to some other devices. So that is formed by IEEE, FCC, CISPR, ANSI, RSS, European nation, and HC. It's also European. So if you see this image, so whatever signal that comes in to your input side, so it should filter all your noises or unnecessary interference in your line. It got to be filtered and it got to be sent out as a clean signal. That's what the standard committee does. So, EMC. EMC is the ability of the electrical equipment and systems to function acceptably in the presence of radiation. EMI. EMC is electromagnetic compatibility. It is nothing but the compatible of your device to work properly under any kind of radiation. Or sometimes they will have something like up to this volt per meter, like 10 volts per meter field, my device will withstand and sustain and work properly. So that kind of test is EMC test. And the next one is EMI. EMI test is an electronic emission that interferes with most of the components like systems or the neighboring electronic devices. That is nothing but the emission which is made out of your device. The first one is it should withstand within any radiated environment. That is how long it can withstand. Or the second one is how much it will emit and make the interference. So the compatibility test it is also called as immunity test. It has radiator test and the conductor test. And the interference measurement happens is also called as emission test. That is radiated as well as conducted. So the EMC test, the immunity test happened radiated way. So the radiated immunity test, it is nothing but how did it happen is your EUT will be in the middle of your anechoic chamber. Anechoic chamber is nothing but it will never radiate anything, or it will never diffract or reflect anything in their walls or on the floor. So that is the anechoic chamber. So the pictures which I have shown is the anechoic chamber, and the EUT is placed in the middle, and with the reference antenna which is on the pole, the emission which is coming out of the device is measured and it is given to the spectrum analyzer. Then they'll plot the graph and they will make it as a document for the standard group committee. So it involves the EUT to strong radiated immunity and measure the performance of the EUT till the end of the test. So this is radiated immunity test. So this test is like the emission is sent out from your antenna. So the complete anechoic chamber will be having the radiation like 20 volt per meter or 10 volt per meter, something like that. So your performance of the EUT will be monitored till the end of the test. Then it says like the EUT can withstand up to this level of radiation. And the next one is conducted immunity. It is done through conducted power or conducted signal. So if you see in the bottom picture, the EUT, from the EUT to the EUT, the power will be connected. So the circles, the one of the circle which is connected to the RF power amplifier, that is connected to the signal generator. So the signal generator will generate the signal, RF signal, and it will send it to the amplifier. So we need to change the amplitude of amplifier amplitude, and depends on the standard, and then it will be sent through the cable and that will be given to the EUT device. So the RF power meter will measure the RF signal which is sent through the cable, and you need to monitor the EUT performance, and you got to certify it that with this much radiation through the conducted way, the EUT is able to work, able to process good. And there are some more immunity tests. Those are ESD test. All of you know what is ESD, like electrostatic discharge. Sometimes if you touch some electronic items, like any electronic items, household items or anything, you will feel a shock. So that is called electrostatic discharge. So for standards or to get the standard certification, we need to have this test also have to be performed on each EUT, and they will give a certificate for this. So the electrostatic discharge is the process of testing the device resistance to the electrostatic discharge. So the gun which I have shown above or the below, which has the pointed tip, that shows the that has the conductor tip. So if you keep the tip on the EUT, that will emit the electrostatic discharge. So you can set like 1 pulse per minute or 10 pulses per minute or something like that. So you got to test your equipment and you got to get the certified. So the ESD occurs when two electrically charged objects come in contact with each other or involved in electrical short or dielectric breakage would happen, resulting in the sudden flow of electricity. So this test, we need to have two different kinds of test. It is contact discharge and air discharge, because the discharge could happen both when two cables or two power cords are supposed, if they are together, so that could cause the contact discharge, or sometimes if you go and touch the EUT, that could cause the air discharge. So this gun which we have two tips, that will produce both the contact discharge and air discharge. So this is the voltage level, that is 8 kilowatts for the contact and 15 kilowatts for the air. We use to test in the lab. And the next test is surge test. Surge test mainly in the outer world could happen because of lightning or thunder or some toggling of the power switches. That could cause your surge default, and no, it may damage your system. So the objective of this test is to evaluate the performance of the EUT under high energy disturbances on the power or interconnection lines. Interconnection lines are nothing but signal lines. The disturbances being caused by over voltages from switching and lightning transients. So the bottom are the few examples that could cause the surge default on your system. Power switching events, insulation faults on the power grid, nearby switching loads, fuse blowing, nearby lightning strikes, the poles nearby to your device. So roughly, if we take a survey, if you connect a typical product to a residential AC socket, we receive 3 times rated 6 kilowatts power surges every year. So this surge also tested in the lab. This surge is usually applied to AC both and DC inputs and also to the signal ports. The surge pulses are usually coupled directly to the signal or carefully defined source impedance. So there will be a CDN, and the CDN will be inside a decoupling CDN. So that will have 3 lines, that's nothing but line, neutral and ground. So we will be sending the signals in 2 ways, either from line to neutral or line to ground or neutral to ground, that is applied to the EUT. So if the EUT withstand all the surge pulses which we give in the power cord or the signal port, then your system is passed. So the surge involves lots of energy. So it could easily damage your system or easily make it die. Next is EFTB. EFTB is nothing but it's a fast pulse. It's a transient signal within a fraction of seconds. So electrical transient, fast transient is the full form of the EFTB. Is an attempt to simulate switching of loads at your workplace. So toggling of electrical switches, or bundling cables could do that, or switching loads, fluorescent lamp blast. It is like a burst signal that is delayed within like few seconds. That could happen multiple times, but it will be within fraction of seconds. So in the lab, on the top of the slide, I have given the CDN, the clamp, the capacitive clamp. So the power cord or the signal line which will be placed underneath the the metallic shield, and then the EFTB pulse will be given to that shield. So we go to monitor the performance of the EUT. As I said, for all the immunity, the EUT got to withstand. So the EUT got to withstand for this pulse, and it get through the standards. Let's go to the EMI test. EMI test is, it should never make any emissions up to certain level, beyond certain level, sorry. So each country has its own emission limit. So if your device is emitting beyond that limit, your device is not going to be shipped inside that country. So how do the emission test is performed? This also performed at two levels, like radiated emission and conducted emission. So for the radiated emission, it is measured in the anechoic chamber of the electromagnetic field. That is nothing but the emissions which is caused or which is coming out of your EUT. So that emission will be recorded in the spectrum chart, and that will be imported to your document, your device document. So we have different criterias. Like on the top of the PPT, I have said class A or class B. Class B devices, or everything is residential devices, that has its own limits. And class A is non-residential, it is nothing but industrial. So that has his own limits. And next is conducted emission test. It is to monitor the noise current or the signal generated by your DUT, device under test, that propagate through your power card or the signal lines. Sometimes your EUT can work, as I said, beyond the dynamic range. So that could cause some ripples or some reflections at your EUT side that could be sent through your cables to your source side, or maybe if it is happening at the power supply side, that could reflect back to your AC supply, the main supply. So the test will be conducted on the cable, on the conducted way. That's why it's called conducted emission test. So by default, this test is performed like from the DUT, the port under test, whether it is a power cord port or a signal port. So the port under test will be given to your LISN, and from the LISN, it will be connected to your spectrum analyzer. So the LISN, which is always impedance matched, so that will have a directional coupler inside. So the directional coupler will send out the altering current that is happening in the line through your cable to the spectrum analyzer. So the LISN which splits both, and you can measure the noise which is coming out of your system. Okay, so far we know what is radio frequency, what is compatibility, EMC or EMI, how do they test, and how do they do everything. So let's see how this RF is going to help in our biomedical field. So far in the biomedical industry, we have many devices by default so far. So these are some example devices that I showed in this picture. Okay, so these devices, so now you may come up with a question, or you may get some questions like, how do these devices related to RF field? So it is nothing but the devices are not performing just to capture the signal and just sending it out. It's not like that. So there is some network communications which is going underneath every devices. So that could sometimes cause emissions, as well as it could be affected by any radiation. So even the committee or the association I said before, they have a separate category for the medical devices as well to measure their frequency limit and to approve it. Because the end user of our medical devices, it's not going to be any non-living thing, it's a living thing. So we got to be even more careful. So the network, which will be explained under the name of BAN, that is body area network. So first we are going to see what is BAN and what is the IEEE standard. It is the international standard, but there are many standards depend on the country limitations. And how do BAN implementations happen, and what is the summary? Okay, so what is BAN? The body area network provides the communication link between our body to the end user. End user is doctors or some medical advisors. So it takes in and around the body. Allows the communication between sensors, actuators, and processing elements. So we will be having the hubs in our body. So in the bottom picture, there is a human body, and you can see the 1, 2, 3, the dots. So those are the hub points. Those are nothing but the joints or the easily accessible points all through the body by all the sensors and nodes. So hub allows nodes to be simpler. Nodes are nothing but sensors, have a longer life, and be less costly. So as I said, the standard for the medical devices is from the IEEE. So that is under the category of 802.15.6. So the purpose of the proposed standard is to provide an international standard for a short range devices that has low power and highly reliable wireless communication for use in close proximity, that is inside and to the body. Okay. So I just want to go from a little basic, like the body tissues. So we have connective tissues, muscle tissues, nerve tissues, and epithelium. So all over the body, so these are the 4 different kinds of tissues wherever you see. So the default thing for the biomedical engineer is to, using the sensor, we need to sense the signal from all these tissues, depends on the patient problem. And then you got to manipulate the signal, and then it got to be broadcasted outside of the world. So the possible hub points from the above body types. So by default it is wrist or necklace hub or belt or on the shoe. So this is the band architecture. As I said, hub is the midpoint and the nodes are the sensors. So the nodes will communicate to the hub and the hub will process the signal or the any abnormalities of the abnormal functions of the body, and then it will communicate to your nearby wireless device, and then it will send it to the medical group. So the second point is sometimes just one node should cover multiple vital signs. Like if you have a sensor on your heart or on the liver side, liver area or somewhere, so that should communicate both with the neighboring nodes as well as to the hub. So that is the another way of architecture. So this is the three layers, physical layers that happen in the band architecture. That is, from the body, the sensors will receive it and it will send it to the physical layer. That is nothing but microcontrollers through sometimes it could be wired or sometimes it could be wireless, even inside your body, from the sensors to your hub. So that physical layer and then to your MAC access control. So that communication between the sensor and the the microcontrollers, that could happen in the narrowband signal or the UWB or the HBC. So NB is the narrowband channels. So these are the narrowband channels that are available right now and under usage, and that is having the data rate which I have given in the chart, and the UWB is the ultra wideband. So ultra wideband which covers both on and off signaling or sometimes modulation signals, and I have given the data rates for that too. And what is HBC? Human body communication. So the electrode in contact with the body is used to transmitting or receiving an electrical signal through the body. Sometimes if the patient is so critical, or it depends on the patient, as I said before. So if the patient is so critical and sometimes the action could be done remotely, in that case the medical group or the doctor, their personal doctors, physicians, so they will have the control through this kind of communication, HBC, and they will send the signal from the hospital to the patient microcontrollers, and then it will be inducing the signal or inducing the therapy or whatever it is to the patient. So this could be done wireless in a wide range. So this is the data rate for that. It could be done up to megabps. So what is the MAC features? So even this question could arise, like why do we need to send these signals to the MAC phones and then to the medical group? Directly it can send it to the medical group or get some, some emergency contact or something like that. Nowadays it is done with the nearby mobile devices. For example, why do we have this kind of communication? Because it supports quality of service. It has improved the communication support up to microcontrollers band. It can communicate, and also it can support the emergency communications, and it supports the hub to node communication as well, and it's a strong security and macroscopic and microscopic power management and coexistence and interference mitigation. That is nothing but if the patient is having a fits and suddenly his heart rate went down. So each of the sensors will sense everything and then send it to the cell phone. So it will record everything because everything happens every second. So the heart signal will be recorded, as well as the total body is shivering and the temperature is going low or something like that. So every sensor signals will be monitored at once. So that is called interference mitigation and coexistence. And you can set up the priority mapping also. So, for example, let's take the pacemaker. It is a medical device. So it helps to find the heart failure, heart rhythm management, or hypertension, diabetes, Parkinson's disease, epilepsy, mood detection, or pain management. So any kind of symptoms like this could be sensed by the sensor, and it is easily given to your supporting device, and then it will be sent it to your doctor. So what is this definition of the therapy? So it can sense. By default, the body area network can sense the signal, like mechanical, electrical, or chemical changes, or any kind of changes it can sense. And also it can process with therapy. Not only all the sensors or the medical devices which are in the market only helps to find the emergency situations and then send the information and then call the emergency and then come to pick up the patient. Not like that. It is also used for therapy purpose. So this therapy is done by a software which is inbuilt in the microcontrollers. So like the insulin pump. So if the sugar level is improving, so if the patient is not checking all the time with the poking pumps, so the sensor will monitor the the insulin or the blood sugar level, and then it will automatically check with the software. If it belows that level, it should send the insulin. It should send the signal to the insulin pump, and that insulin pump will inject the insulin inside the body. So it does not need any medication or any medical advice or any patient to deal with that. It will just automatically happen. So this is also done as a therapy and present to doctor. If it is not working, or the insulin is out of stock or something like that, or if it is emergency, even if I pump the insulin inside, the sugar down level is not going down, it will again sense, and if the doctor need to be present at that situation, it will send it. Allow doctor to stimulate. As I said, the HBC communication, it will allow the patient, it will allow the doctor who can induce the insulin more from the remote by the doctor. On the medical devices like pacemaker, implantable cardio defibrillator, spinal actuators, insulin pump, continuous glucose monitoring, deep brain stimulator, external or internal hearing aids, retina implants, or muscular signal replacement. So, we have been talking about sensors and actuators. Sensors are nothing but it just sends the signal and then it sends the information back to the processing unit. But the actuators are mainly used for the therapy purpose. It will just, if it is an old patient, if he is having an epilepsy problem, so sometime if he goes out of his mindset, or if he goes sometimes fade, it will just create a short pulse and then it will stimulate your brain process and then it will bring him back. So that will be sensed by the sensor, but along with the sensor, on the node communication, extended node communication, so we will be having both the sensor and the actuators. So the sensor and nodes actuators will communicate each other, and then according to the programming, it will just send the signal and then helps the patient. So summary. Body area network standard will allow medical device intercommunications. Medical experiments in BAN enabled diagnostics are proving to have high therapeutic value. There are many worthwhile applications happening in the biosensors. Some will provide better healthcare like quick patient recovery or any new therapies needed if the old therapy is not functioning properly. Some will greatly increase convenience for the users, and some have the critical apps. Example, for the war fighters, if they have a physical monitoring device on them, that time it will have the critical apps, so it will send the immediate response to the emergency department. And physicians wish for less wires in patient diagnosis environment, especially in critical care. So this BAN helps us the wireless communication, and it will be updated with the doctor on his doorstep. The body channel model is challenging and it have lot of contributions, and many organizations are coming up to improve more. For example, if you see this, the RFID diagnostic skin patch, it's a skin patch. This is nowadays it's common, everybody can have it, and it will warn you if the fever exceeds 101. So you will get the warning message from the sensor to your cell phone, and then you can take the medication accordingly if you're a normal patient. Okay, So let's take a quick demo.
Embedded system is everywhere nowadays, from phones to cameras and even cars. So, what's the next generation of embedded system that society needs? The field of wearable, especially body area network, looks promising. What is body area network? Body area network is a wireless
Hello, Srividya. Hello, Srividya. Srividya, are you there?
network of wearable computing devices connected to a cloud networking all around the human body to serve a variety of applications. It can be made up of ECG sensors, body temperature sensors, hearing or vision implants, heart rate sensors, and blood pressure sensors. These sensors on the body is then connected to the cloud through a personal device. VN functions mainly uses Internet of Things concept. The functionalities can be divided into healthcare, defense, sports, and lifestyle. In healthcare, VN is used to monitor and detect abnormalities in the patient's health. The military uses VN to locate the lost personnel using GPS, and in military personnel's health monitoring. In sports, coaches can utilize VN to monitor their athletes. And wearables, such as earphones, provides a means for people to enjoy music individually. The benefits are time, money, and energy saving. No need large machines for patient monitoring. Continuous patient monitoring by medical personnel. Ease the recovery of lost military personnel. Monitor athletes' performance. And helps coaches to plan for competition. Current body area network available in the market is inefficient and bulky. But as the wearable technology gets smaller, lighter, and cheaper, body area network will be an important technology in the future. Thanks for watching.
Dear participants, any queries you can post in Q&A. And some of you posted your queries already. Srividya, can you hear?
Yes, Shilpa. Can you hear me?
Okay, I'll read out the question so you can answer it. What is meant by RF?
Okay. RF is a radio frequency signal.
Yeah, continue.
What happened?
And then, what is the meaning of radiator?
What is the meaning of
Radiator, radiator.
radiator?
Yeah.
Yeah, radiator is nothing but it radiates the RF signal. So the whatever if it is a cable, if you take out the shield in the cable and if you just keep the cable on top of any tower or anywhere, that acts as a radiator.
Next, how do the devices used in RF signal? How do
Steven here.
the device is used in RF signal?
Yes, sir.
You can get the questions from Q&A tab. It is available in your desktop. Yeah. So
Oh,
from the
okay.
detail. Yeah.
Okay. So what is radiator? I think I said. What is SFDR means? SFDR is spurious free dynamic range. So the dynamic range is the threshold level of the system which works normally. Beyond that threshold level, it works with more emissions, like unwanted emissions. So the unwanted emissions are called spurious. So spurious free dynamic range. It is nothing but below the dynamic range. And the next question is, what is RPF? Amplifier? RPF? I don't know what is RPF amplifier. Sorry, maybe I'll get back to this question. What is EUT? EUT is equipment under test. How to do the device is used in RF signal. How to do the device used in RF signal. Because all the medical devices which are used in the medical field mainly comes with microwave energies or sometimes the radio signals, radio frequency signals. So the communication between the patient to the outer world is happened with the radiation, with the emission signals. So that's where the human body devices used with the RF signal. What is the need for human body communication? Human body communication is applicable only for the person who needed very critical care. Like if he is a very old person and if he is already having multiple heart strokes, at that time, if he is getting the next stroke, then sometimes he will be having some kind of medication in his body. So that will be injected in his body. But if that medicine amount level is not enough, then the sensor will sense that patient body situation and then send it to the doctor, and the doctor will remotely, because he know the patient body better than the patient, so he know what is the dose improvement can happen, so he will improve the dosage level from the hospital, so that will be received by your body sensor through the HPC communication, and then it will be treated. That's why we need it. Can you explain SFDR in detail? I think that's what I said. It's a spurious free dynamic range. What about Feedback. No. I think I got to, for the feedback form, I got to ask for Shilpa or the organizer. What about the security of personal data? What kind of ethical standards define? I'll get back to this question by email. Actually, it has more information on it. What type of processor used before the actuator? Before actuator. I have no idea. I'm sorry. I think I'm done, Shilpa.
Yeah, thank you, Srividya, for giving the wonderful session actually. And I like to thank for our management for organizing this webinars. And my sincere thanks to Principal Sir, Vice Principal Sir for giving this opportunity. And my warm thanks to the Revati ma'am, head of the EC department, who supports to take over the session. And my hearty thanks to all the participants who have joined and making the session great success. Thank you, Anand.
Thank you so much for the principal, vice principal, and the HOD, Revati ma'am, everyone in the call, students, for listening to my PPT, and hope you might have enjoyed, and this would help you in future to improve more. Thank you.
Thank you, Srividya.
Thank you, sir.
Thank you for our valuable lecture for the students. Thank you very much.
Thank you so much. You're always welcome.